I must freely admit that on Wednesday I cheated. I walked through that Gauss-Jordan procedure, that method of reducing a matrix to find a solution, knowing what the answer looked like. That makes no sense. If I know the answer, why am I doing all the work? So the question becomes, how do I know what I should be striving to get to? We have a set of preferred forms. As long as our matrix contains entries other than 0, I can rearrange it into this format. If it's all zeros, it's all zeros. I walk away, I'm done. There are 3 criteria for row echelon form. I want to sort it so that any row with non-zero entries is at the top, and any row with 0 entries, all zeros, is at the bottom. The leading entry in any row, that's the leftmost non-zero thing, is further to the right than the leading entry in the rows above. In other words, as we go down, our leading entry moves from left to right. And the only thing under a leading entry is a 0. Now that sounds confusing as all hell. So here's an example. Now you'll notice I did not put a vertical bar in here. That doesn't matter. Whether I think of this as part of a system of equations or just the coefficients. I just want to look at this and go, does this match our 3 conditions? Are there any rows of all zeros? And I don't have to worry about the first one. The first one would say all the rows that have all zeros should fall to the bottom. Not worried about that. The leading entry on any row is right of the leading entries above it. So the leading entry in the first row happens to be all the way to the left. Leading entry in the second row is 1 unit to the right of that. The leading entry in the third row is all the way on the right, but that means it's definitely right of this 4 and it's definitely right of this 2. Check. Underneath the leading entries, I see only zeros. That's condition 3. This is related, in example 1, to the idea of a triangular form. And as I pointed out in example 3, if there was a vertical bar here, then I would have x1 and x2 and x3 in numbers, right? Well, then that bottom row would say no x1s plus no x2s plus no x3s should be 1. Do you want to know any universe where that works? Me neither. That's a set of equations with no solutions. This is also in row echelon form. But there's more going on here. Notice leading entry, leading entry, leading entry. As we go down, they move to the right. Nothing below a leading entry other than zeros. But in this case, I can also say that there's nothing above a leading entry other than zeros. So I've added something. I've added a new condition. Condition 4, all leading entries are 1. You didn't notice that part, did you? And condition 5, all leading ones are the only non-zero entries in their columns. Adding these 2 extra conditions gives me something called reduced row echelon form, which I prefer over just regular ordinary row echelon form. And I promise there's a reason for that. It isn't just because I think it's pretty. There's actually a better reason. I do think it's pretty, but there's a better. On page 14, well, my book, page 14, in section, chapter 1, section 2, example 1, a bunch of matrices. Please notice the 0 rows are all at the bottom. Those are my leading entries, the boxes. Stars could be anything I want. Wildcards, right? My leading entries go to the right as I go down. These top 2 are in row echelon form. I don't know what the box numbers are. I just know they're not 0. Here, that's reduced. It's the same basic setup, but notice what changed are these first 3 numbers. I have to make those leading entries 1. We know how to do that. Multiply a row by a number. Here, same thing. Make that a 1, make that a 1, make that a 1. All of these boxes turn into 1s. But then above those, we do more row operations, more elimination steps to make zeros above as well as below. Row echelon form, reduced row echelon form. And the reason I like reduced over regular is right there at the bottom of the page. Theorem 1. Each matrix is row equivalent to 1 and only 1 reduced form. In other words, there are many different versions of the same matrix that look like this. There's only 1 of these. Reduced row echelon form is unique. I will use that abbreviation all year long. RREF, reduced row echelon form. Like we wrote it right here. RREF. We can talk about an echelon form. We can talk about a row echelon form. There is only one reduced row echelon form for any given matrix. We will often write it as like it was a function. Take a matrix A, and then we can reduce row echelon form that matrix. We get a unique thing. Typically, I will use the letter R for a reduced row echelon form matrix. It's not required. You'll see it in a lot of different textbooks, a lot of different ways. My goal with any matrix is to find either a row echelon form or a reduced row echelon form, because that's going to give me my solution set. So now I have a clearer statement. My goal is to do these things to get it to look like this. Not just do them until you come up with an answer. What's the answer supposed to look like? It's supposed to look like an echelon. However, if I go back and I look at that example 1, I notice something interesting. The leading entries, when I do my echelon work, don't move. I don't know where they're going to be, but whether I'm in echelon form or reduced echelon form, they're in the same places. So it's actually not the numbers that matter as much as their positions. I'm going to give these some names. I'm going to call the leading entries in any given row, I'm going to call them the pivots. Which means I get pivot columns and pivot rows. And the entries themselves are called pivots. So a lot of what we are doing in our matrix manipulation is pivot work. And if you go into Excel, you'll see them called pivot tables. Surprise! That's where it comes from. Whew. So now, there are several questions that remain. Going through the process we went through Wednesday. Do I know when to stop? What are my fault conditions? Now 0 equals 0 doesn't tell me to stop. It just tells me there's a 0 row. I can go down to the bottom, drop it to the bottom and leave it there. I should keep going until I run out of places to put a pivot. That's going to be my new fault condition. Let me do one all the way from scratch. Here is our given matrix A, 0, -3, -6, 4, 9, -1, -2, -1, 3, 1, -2, -3, 0, 3, 1, 1, 4, 5, -9, -7. Oh, that 1 on the end of the third row should also be a negative. Catch that. There. Now, I said it on Wednesday, talked about this as going forwards and backwards. Let me try and figure out why I would say it that way. To get to row echelon form, I want to pivot in each possible column I can put one in. I want the pivots to start as far to the left as I can and go to the right as we move down. I want the things under the pivots to be zero. That's our forward direction. If I'm going to reduce row echelon form, I also want to work above the pivots, and that's the backwards direction. So forwards and backwards. You can do it together, or you can do all the forward part first and all the backwards part after that. I like to do it together. That means I work one column at a time, like I did on Wednesday. In the textbook, this is example 2. They do it all forward and then backwards. That bugs the hell out of me. I didn't write the book, so we'll do it my way because they did it their way already. You can watch that one. All right. So my first question is there a pivot all the way upper left? Damn. It broke. No, it didn't. I can move something there. And you have your choice because we can switch rows. So I'm going to switch a row to put something up there. You could use any row you want. If I'm going to reduce row echelon form, what do I want my pivots to be? I want them to be 1. So let's take the bottom row, which already has a 1 in it, and swap it up there. I am going to interchange row 1 with row 4. This is the downside of doing all of this by hand. I'm going to make a lot of copies of the same numbers over and over and over again as I do my different row operations. So this gives me a brand new matrix The only thing I did was cut and paste. Okay. Now I have a pivot in the upper left corner. Condition number 3. All entries in a column under the leading entries are zeros. Means I need everything under that 1 in the upper left corner to be a 0. These are my elimination by addition steps. So let's eliminate. I want to get rid of a -1. I'll add this +1. So I will take row 1 times +1 and add it to row 2, and I'll write the result in row 2. I'm using that pivot as a hammer to beat away that other row. Since I'm using the same hammer for everything in that column, I'm going to do these 2 operations together. I also want to knock out that -2 here. But I'm going to use this to do it. So I'll say, oh, let's take 2 row 1s. Add that to row 3. Write the result in row 3. You don't have to do these at the same time. You could do them separately. I'm just going to end up copying 3 lines over at a time. If I do each one separately, I'll make 2 copies of the whole thing, right? More paper. Up to you. Now, here's the point. I am going to guarantee you at least once you'll pick this one up. We're doing a lot of hand arithmetic. Sign errors, addition errors, subtraction errors are the bane of my existence. Because you won't know until we get all the way to the very end whether or not you added 1 and 1 and wrote down 3 at the beginning. I need to do this arithmetic. You can do it off to the side. You can do it on a piece of scratch paper. If you're fast and good enough with your arithmetic, you can do it in your head. That's up to you. But notice nothing is going into row 1 and nothing is going into row 4. So those rows are not going to change at all. But I will get a new second row and a new third row. I just added, right? Added these two, and these two, and these two, and these two, and these two. Just wrote down my results. Now I got to do the multiplying by 2. Positive 2 and negative 2 gives me a 0. Positive 8 and negative 3 gives me a 5. Positive 10 and 0. Negative 18 and 3. Negative 14 and negative 1. Brendan, you're looking at me like I just did something psychotic. Talk to me.
So we multiplied and then you either like added or
Multiply and add, multiply and add, multiply and add.
okay.
So this row gets multiplied by 2. This row just gets copied over, and then I add.
Okay.
Yeah. See, I made a copy error. I told you I was going to fuck it up. And then that goes in and becomes my new row 3.
Okay. I would probably learning it. I'd probably write it out again, but
Absolutely.
I see how it's done now. Thank you.
Yes. I just did row 1 plus row 2, right? So it would be 1, 4, 5, minus 9, minus 7, minus 1, minus 2, minus 1, 3, 1, 0, 2, 4, minus 6, minus 6. I will fill scrap paper with calculations like this. And I guarantee you at least once. I just did it for you. That shows you how easy it is. But now, my first column is 100% complete. I have exactly what I wanted. So now I say to myself, can I put a pivot in the second row? Well, there is a pivot in the second row. There's a leading non-zero entry, right? There's a 2. You have 2 choices. You could make that a 1 now, or you could do the arithmetic to get rid of the stuff, leaving it a 2. I find it is never convenient to leave it as anything other than a 1. Because when it's a 1, I know exactly what I need to multiply to get rid of stuff. I need to multiply by the opposite of these other numbers. So I'm going to start with my first comment being this is where my next pivot should go. I'm going to take row 2 and multiply by 1/2. And then I'm going to write that answer in row 2. So I get to copy my matrix down again and only change row 2 this time. What's my new row 2? Ta-da! Now again, if I was only working forwards, I'd have 2 more elimination steps. Do the stuff under the pivot. I want to do it all at the same time. So I'm not going to only work down, I'm also going to work up. I'm going to do 3 eliminations. I want to get rid of all other numbers except the pivot. So to get rid of this positive 4, I need a negative 4. Use my pivot and add it to the first row. To get rid of the 5, I need a minus 5. Use my pivot, add it to the third row, write my answer in the third row. To get rid of a negative 3, I need a positive 3. Using my pivot, add that to the fourth row, write my answer in the fourth row. I write that down first before I start doing any changes. And then I say, oh, I'm going to have a new matrix. The second row is not being changed. Row 1 is being changed, row 3 is being changed, row 4 is being changed, but not row 2. So I copy that one exactly down. Now, arithmetic time. Please notice this 0 is going to get added up and down that first column, yes? When you add 0, you don't change, do you? Nothing I do with row 2 is going to change column 1. My pivot column stays in the right form. Once I've done it once, I don't have to do it again. So now I work my way up. Negative 4 and 4. Negative 8 and 5. Positive 12 minus 9. Positive 12 minus 7. Yes? You'll notice I didn't write it over on the scratch pad. Joy, you're looking at me like I'm out of my mind. Do I need to write it off on the side? Sure, absolutely. So I have 0 minus 4 minus 8 plus 12 plus 12. I multiplied by minus 4. Then I copy this down and I add 1, 0, minus 3 plus 3 plus 5. You got to do 2 more of those, people. So I multiply by minus 5 this time. Oh, ho, ho, ho. What happens to this row? It's all zeros. That's okay. Allowed. One more time. Multiply by 3. So far, so good? Not short. Works, but is not short. Row 3 has no non-zero entries. Where should it go? Which means I do a row swap. I swap row 3 and row 4. However, that means there's a pivot in what is currently row 4 that should end up in row 3, yes? The leading entry here is a negative 5. I'm going to end up having to do 2 steps. I'm going to have to switch them, and then what am I going to have to do? Almost. From what? Add, I can't just add to a row. I have to add a multiple of something. Aha, I don't want to multiply by 5, and I want it to be negative, because I want a positive 1 when I'm done, right? So really, there are 2 steps going on here. I need to do row 3 swap with row 4. And technically, right here, I've reached row echelon form. Almost. Row echelon, right? Because under each of my pivots is nothing but zeros, and the leading non-zero entries go from left to right. And all the rows of zeros are at the bottom. That's row echelon form. What's that extra R stand for? Reduced. So there are 2 more steps. There's make the pivot a 1, and then clear the rest of that column. It's not only below the pivot, but above the pivot. 0. There's my make it a 1. You need to give me 2 more row operations. What's my hammer? What's the pivot I'm using? What's the fist that knocks the other stuff out? Pivot row. Okay, wait a minute. Positive 3, right? But I'm using row 3. That's the pivot row at this point. My 3rd pivot over, I'm using row 3. So I need to get rid of this. I take positive 3, row 3, to add to row 2. Exactly like you said, Jack. What about row 1? I got to put a 0 here. What am I going to multiply by? Exactly, Shane. Multiply by the opposite of the thing where I want a 0. I multiply by the reciprocal of the thing where I want a 1. Again, off on my side scratch. That's just going to make that a 3. Everything else in that row is a 0, right? Which means everything else in that row doesn't change anything above it. I hope this arithmetic is clear. The only thing that can be changed is this number, because that's the only non-zero entry in this hammering. Same thing here. I'm going to get 0, 1, 2, 0, -3. Then down here in row 3, and a completely zeroed out row 4. Phew. Yes, sir. Then it would be done. 0 equals 0. That doesn't tell me, does it? And there's only really one set of equations that could ever give me that, right? 0 equals 0. Why would you start with a set of equations that said that? I don't know what problem would lead me to that, but the 0 matrix itself is a useful thing in a slightly different context. It doesn't often show up in solving systems, but it shows up when we start to think of matrices as objects themselves. An array full of zeros is a useful array as a starting point. Other questions? Yes, sir.
Would, like, so based on the steps that we did, are there other possible ways to get the same answer? Even if it
Absolutely.
be like longer?
Oh, yes.
Okay.
The only reason I chose this method, this is what's called the Gauss-Jordan method. The handout is on our Canvas page, walks through a smaller example. This is the fastest version of this algorithm.
Okay.
To my knowledge, other algorithms are n cubed, where n is the number, a number of rows or number of columns.
Okay.
But it's also very dependent on how many things get eliminated at any given step. You know, I knocked out a whole row, didn't I?
Mm-hmm.
I got lucky. At worst, because each of these additional side calculations are so long, yeah, this is big O of n cubed. Making this faster can be done. It requires subdividing your matrix and trying to work in those subdivisions. It's harder,
Yeah.
in my opinion. And even within those submatrices, you're still doing this. So, yes, I could, but this is probably. And by the way, if you did the operations in a completely different order, you might take 37 pages to do this. You'll end up here. This matrix version, this reduced row echelon form, is the reduced row echelon form for this matrix. From here, you must end up here. Only one. More questions? So now I have three pivots, three pivot columns. Let's make an assumption. That there really should have been a set of equal signs here. This is a system of equations. With that assumption in our hand, how many x variables do my equations have? An x1, an x2, an x3, an x4. Then there's the equal signs, and those numbers all the way on the right are the numbers on the other side of the equal sign. So I have x1 through x4 here. I want to divvy these up into two separate categories. The variables that go with my pivots are called basic variables. And the other ones, any variable in a column that does not contain a pivot, is called a free variable. Some textbooks and some internet sources, instead of using the phrase basic variables, use leading variables. Well, that makes sense. Those are the leading entries in our rows, right? I'll buy that. So what? What does this tell me? Do me a favor and take this set of rows and turn them back into a set of equations. Wait a minute, I know number x1, number x2, number x3, number x4 equals the number on the other side of the equal sign. Write out three equations. Why do I only need three equations? Bottom one's all zeros. It doesn't do me any good. Those are the equations I end up with, yes? Let's go one step further and isolate the basic variables. Take the free variable, put it on the other side. Because I want to consider all of these together, I'm going to put that little brace there to remind me, hey, all of these go together. I found my solution. All look at me like, what do you mean? What I have in front of me here is infinitely many solutions to this set of equations. Jack, give me a number. Say again? Okay, if I put in pi for x3, I get 5 plus 3 pi, negative 3 minus 2 pi, x3 equals pi, and x4 equals 0. Marcia, give me a different number. Then here I get x1 is 50. Here I get negative 33. Then x3 is 15, and x4 is 0. Your free variable becomes a free choice. Most of the time, mathematically, we'll replace that with a letter, a parameter, and we'll call this a parametric solution set. And here is where I specified that parameter by writing in my choice for x3. This is a parametric solution set for the set of equations we came up with in the matrix A. When I get to reduced row echelon form, even if it isn't a perfect triangle, I've solved my system. When am I going to have no solutions? When one of these equations is invalid. 0 equals 15. Ah, that's never true. Walk away. And if I have an entire row of zeros, then I'm going to have more variables than I have equations, right? So I'm going to get infinite. When am I going to get exactly one solution? What in the matrix or in this set of equations would tell me there's only one choice? If I finish all my work, there are no free variables. Then there's nothing for me to choose. Here's x1, here's x2, here's x3, here's x4, I'm done. Now remember, I said earlier that the pivots don't change position, which means once you've written down the set of equations into a matrix, if I could somehow figure out in advance how many pivots there were, I could tell you whether you had one solution or more solutions or no solutions. I knew where all the pivots were, how many there were. Unfortunately, there isn't a nice, easy way to cheat and do that yet. We'll figure one out eventually, but it's much more complicated. If As I said earlier, we have any rows that are all zeros on this side and then something not zero, that's got no solutions. Theorem 2 in our textbook writes that out explicitly. A linear system is consistent. Is consistent means has one or more solutions if the rightmost column is not a pivot. If the rightmost column is the first time you see a non-zero number, then you get no x1s, no x2s, up to no x whatevers equals 3. That's not going to work. So really, I want to look at the pivots and hope that they're all on the coefficient side. None of them are on that other side, on the augmented piece. That's what we did. Please notice, in the 47 minutes of class that has elapsed so far, I did one large example. Are these fast? No. Is it a deliberately straightforward algorithm? I think the answer to that question is yes. And if it's a straightforward algorithm, it should be codable. Which means eventually I won't have to do it at all. I'll push a couple buttons and it'll be done for me. But I should be proficient in it and make sure I can check things. The reason for that, one of my fellow graduate students at the University of Pittsburgh used a giant matrix to solve a problem in differential equations. 29 rows, 29 columns, plus the augmentation. And the things that were in his matrix weren't numbers. They were functions. Which meant you couldn't just throw it in a computer and hope and pray. Unless you spend the $1,300 for the, original software that Wolfram put out called Mathematica, or Maple, or one of those big computational programs. And then it'll do it. It's called a Wronskian. It is not short. He threw this into the computer mainframe at the University of Pittsburgh. 5 minutes later, the algorithm popped out the answer. I want you to think about that. 5 minutes of computational power. Not short. It took him a month to check it by hand. I really want the algorithm because I don't want to do this for a month for anything. By the way, the reason he was doing this, he was working in biological modeling, and the 29 equations he had come up with were the chemical balances for the chemistry of the liver. And what he figured out is that as long as these chemicals stay in balance, that's a healthy liver. And when they're out of balance, that's a problem. So he built a device about the size of a can of soda, hooked it up to a bunch of chemical tanks, and was able to use it as a replacement liver, keeping people alive on the table, waiting liver transplants. He had 4 patients alive. Useless crap. I'm never going to use it anywhere. Love matrices. I told that story in DiffEQ last year. So there you go. All right. I will see you all on Monday. We will have more to say about this. Have a wonderful weekend, everybody. Drive safely.